Thank you. And thank you very much for inviting me to give this lecture and the opportunity to talk about supercomputing in a data science series of lectures. And so I thought I start with what people normally recognize supercomputing for, namely the fact that these are very fast machines and the top 500. So this is the simplest way of looking at the field. It is a plot that I took from this top 500 list, and it has been tracking the fastest 500, the fastest machine in the world, delivering a specific benchmark called the Limpag benchmark that's solving a linear set of equations, dense matrix equations. And then the cumulant of the fastest 500 and the last of the 500 on the list at any given time. And what you can see, a line in a logarithmic plot, is exponential improvement in performance. And it turns out that some of the applications, particularly in material science, the field I've been working in, and quantum chemistry, actually have been tracking this. So the first sustained teraflop, so that would be a billion operations per second, was somewhere around the late 90s. And then the first sustained petaflop, which is a quadrillion operations per second, was sustained about 6 or 8 years ago. And you can also download the application. So I ran it this morning on this iPhone here, and I got 1.6 gigaflops in performance. And the laptop I estimate that I'm on, I didn't have time to run it, is around 150 gigaflops. So this would have been the fastest machine, at least on this list, at the beginning in the mid-90s, around the time when I did my PhD. And it turns out journalists are fascinated by this, and many people, because the numbers, the floating point operations we're talking about, when you write them out this way, these 64-bit numbers, they look very cumbersome. And then when you think about it, the petaflop is 10 to the 15 of these in a second. So if we wait for a few more decades, we actually reach Avogadro's constant and truly macroscopic numbers that we do in a second, or numbers of operations. Now, another way to look at it is that the fastest machine somehow represents technological leadership. That's at least how the US government and many governments around the world want to see it. And what I show here is the red dots are actually non-US machines. So these are all machines somewhere in the US, but there were always a few in Japan. This was the Japanese Earth simulator. And this basically introduction of this machine caused some effects in the US. I remember I was working at Oak Ridge, and this is when even my career then changed into computing from material science and nanoscience. And what you see here, the latest dots are Chinese systems that seem to be dominating the market. And again, so Japan is one thing, but when China is up there, then it is a real threat. And this is what then led to this finally. So the community has been talking about this exascale initiative for a while, but it didn't get much attention. But when the leadership in the US is under threat, then we come together and have our president sign an order. And this was it, the National Strategic Computing Initiative. But seriously, it is going to be known to a lot of scientists, because you see here the three agencies that pretty much fund, apart from NIH, which somehow is involved, but mainly DOE, NSF, and DOD are involved here. So many US scientists will see this somehow in their funding. what you see, apart from how they are going to do it, some of the things that the strategic objectives are really clear. They are things like exascale computing, but really capabilities across many applications. They want to see coherence between modeling, simulation, and use of data analytics. So it's believed that there is a convergence of data science and high-performance computing going to happen in the next 5 years. And but there are also things like the limits of CMOS and continuing to improve scientific computing performance beyond the limits of CMOS. So I will try to explain in a bit more real terms during this lecture what these terms all mean, and that there is actually some substance behind this. But before I really go on, I want to get back to this improvement in performance of the top system. So when you draw a line between these, and these are really sustained performance in applications, you see this is a 1,000-fold increase in performance every 10 years. For material science and chemistry, if you now turn to a different domain, climate, you can probably turn to any other domain and find something. The reason I turn to this one is particularly, I will cover it in the lecture, but it's also because there is another institution, the European Center for Midrange Weather Forecasting, that has been tracking the performance of their application on the systems they have. And they are systems that more or less track the top 500. And when you draw this line and then do the math here, then you will see it's a factor 100 increase in performance every 10 years, which is still a lot over many decades. That adds up to a lot. But when you compare it to the other one, then you can say, well, has the efficiency of these climate applications decreased a factor 10 every 10 years? Or what is going on? And so what this indicates is that, of course, looking at things is a little bit more complex in reality. And so what I would like to do after this introduction, I would like to cover a real scientific use case, making a real case why we need to continue to improve performance. So this is not just something because the Chinese have it or something else, but there is a real scientific case. I'm not going to cover 10 application areas. I will focus on one. Then I will go into the evolution of computing systems, and I will have to do this because from this then I derive what I believe is the real challenge, and that's the area of software that I will talk about how I believe that these software challenges need to be tackled. And I think we're fine if we do what we have to do in that area. So but first the motivation. So this is a simulation from the European Center for Midrange Weather Forecasting showing a hurricane that is predicted here to make landfall. It turns out, I think I don't have to say much here when I present this in New York. This was October 25th, 2012, when the prediction was made, and it turns out this was Hurricane Sandy that I believe about 5 days later or so made landfall here, and it's in everybody's memory. Now, why is this important? Well, if you run these simulations, depending on the initial conditions, you can have the hurricane either turn or go out in the Atlantic Ocean. And it turns out most weather forecasts here in the US predicted that it would actually turn right. And it was ECMWF's prediction. And both simulations I'm showing here are from the same model, but slightly different, varied initial conditions. And it was theirs that really predicted the right storm track. And the economic value of understanding 5 days in advance where such an event is going to happen does have an impact, a huge impact on how you plan evacuation along the East Coast. And I think alone this probably paid for the whole of ECMWF, the investment over the many decades they existed. So this is one example. Typically, when we talk about these climate models, we talk about the resolution of the grid on the planet. And we have what is called a reduced Gaussian grid in this model. And the model itself is then, this is then a slice. It's a stratified model, so you have layers and grid points or columns. And we are talking about the resolution is the distance between these columns, which in the model we just saw is of the order of 30 kilometers. And the distance between layers, depending on where you are in the troposphere, is somewhere between tens of meters to hundreds of meters. Now, why do we need to increase the resolution? Well, one thing is if you're living in a country with mountains like Switzerland, if I plot, this is Switzerland with the Swiss Alps. If I go to this low resolution of 30 kilometers, I can see there are mountains, but I don't see the valleys. And if you want to make predictions relative to that area, you have to crank up the resolution. At least it turns out to 2 kilometers. So you have these valleys where we have these winds that we call them in German Föhn winds or air blower winds. They are, I think there's a similar wind in Santa Ana, yeah, on the west coast. So being able to predict these winds in these valleys is key to predict what the weather is going to be like. And so weather services that have to deal with these type of situations, they are already today, they are running, like MeteoSwiss, they are running nested models. So they take the low resolution model that we saw before from ECMWF and then run their high resolution models in nested, taking the initial and the boundary conditions from the global model. And they produce, again, they produce daily weather forecasts for air traffic control, and so on. So MeteoSwiss up to March has been running this 2-kilometer model. And why don't we go to higher resolutions? Well, all the mathematicians in here know that if I talk about doubling the resolution, I talk about 4 times as many columns. And then because I'm resolving with higher resolution, I'm resolving higher, lower frequency or higher frequency phenomena. So I have to increase the number of time steps or double the number of time steps. And so overall, doubling the resolution is somewhere around the factor 10 in performance increase. So if we go from where ECMWF is today to what MeteoSwiss wants to do, it's a factor 100. And to where most models want to be, it's probably a factor somewhere between half and 1 kilometer. So it's somewhere around a factor 1,000 compared to what we had today. And you can even make this quantitative, that these are not arbitrary numbers. So here I'm picking two of these valleys in Switzerland. This is the Reusstal and then the Leventina over there. And you plot the wind speeds, average wind speeds across the valley for different times. So this is the measured wind speed. This is the forecast at 2-kilometer resolution. You can see you get it qualitatively right, but not quantitatively, and improving the resolution a factor 2 or increasing the performance a factor 10 will get it quantitatively right. Now, it turns out that not just for orographies like we have in the Alps, but even if you are over the ocean or over some flatter lands and you are just looking at thunderstorms and how they form, it turns out you need, and this you can show empirically in the simulations, to get a proper description of these thunderstorm clouds or most clouds in general, you need resolutions around 0.5 to 1 kilometer. And in addition to this, you need the so-called ensembles because we have this uncertainty in the initial conditions. We need to run this, many of these simulations at the high resolutions. So these are the ample reasons why you basically, and that's another example. This is in Switzerland. The forecast at 2 kilometers sometime last summer for precipitation across the country. And we are looking at one spot here. So this is a single trajectory forecast that they've been able to run up to now. And this is an ensemble forecast that we were testing last year, but it was not in operation. And you can see most ensemble members predict more or less the same thing, but there are a few that would predict these extreme events. And then when you compare what happened later on, so it turns out the precipitation was much higher. You can do the statistical analysis, and the fact that you had higher precipitation then led to these, again, landslides there that were causing some damage. Now, the predictions cannot change what is going to happen, but at least they can prepare you. And they prepare you for things like hurricanes, but they prepare you for very mundane things that still cause a lot of damage. So the value of this is very big all around the world. And so what MeteoSwiss, the partner that we have and that we are working for at the Swiss National Supercomputing Center, is in a mode of transition going from their current 2 kilometer resolution operation to 1 kilometer, and then adding the ensemble simulation sometimes this year. Okay, so before I go on and look at the software behind this, I want to now make a brief excursion into computer systems. Turns out the first numerical weather predictions were made by a British mathematician, Louis Richardson, and he was using, this was around the time of World War I when he was using slide rules at the time, and probably realized how painful this is, and then was proposing a computing factory where he would assemble 64,000 people in a globe, and then have a conductor in the middle, conducting all these computations. And you laugh, but this looks very similar to a Cray 1 or Cray 2 system. And so obviously he had a hunch of what was going to happen. And we know, of course, in the meantime that electronic computing developed starting with Atanasoff Berry in Iowa State University, and about the same time Konrad Zuse in Germany, and they had the 75-year anniversary of the Zuse Z3 system. Now, I know my colleagues were in Berlin this week. And then in the US, it was Eckert and Mauchly that then implemented this UNIVAC system, and then John von Neumann, who wrote a mathematical abstraction of these systems here. So what we call von Neumann architecture is really not his architecture, but it was the invention of Atanasoff Berry and Konrad Zuse. And to my German friends, I always have to remind them that even Zuse did commercialize his machine, the Z4, and he did it by leasing it to ETH Zurich. So that was the first academic system in Switzerland. And the interesting thing is the reason they bought the Zuse 4, or not bought, they leased that system, was because prior to when they were investigating which system to buy, they actually talked to John von Neumann and some other fellows here in the US. Von Neumann was a graduate of ETH, so that's why I guess there was some relationship. And he recommended not to go with the system that were available at the time, and that the SUSE system would be more reliable. But the relevance of all this is, of course, the von Neumann abstraction, which is basically telling us that at the time and almost, until recently, we could describe, we would not have to worry about the details of how a computer is made up, just acknowledge that we have memory, that we have a processing unit, and we have input-output units. And so the difference between this abstraction and the Turing machine is essentially that you have finite memory size. If the memory was infinite, it would even be a Turing machine for which we can prove a lot of interesting theorems. It turns out then over time things became a little bit more complicated, but the abstraction is general enough. For example, you had, in order to keep up with the speed of the CPU, the builders of computers had to introduce a memory hierarchy. And unless you really worry about the last bit of performance, you could more or less ignore this and still look at it as a von Neumann system. So this was until maybe 15, 20, or well, 20, 25 years ago. Then you had, since the late 80s, you have parallel computers develop, and these are the computers we have today. And what I'm trying to show here is that parallel computers are much more complex, and they can have very different interconnect. But the reason most of you don't know about the details of the interconnect is because, again, for these systems, you can formulate an abstraction, which is the so-called bulk synchronous model that was introduced by Valiant in 1990. And the way this works is you have compute components, which are essentially von Neumann machines. And then you have, and this is now independent of what your interconnect looks like. And the interconnect is just abstracted with a router. And then you have some, and again, this goes for any of these machines. And then you have some facility for synchronization and some time that it takes to synchronize all the processors. And that will give you one of the time scales and the granularities of your parallel computing. And so this is the reason why those of you who have experience and used MPI, all you need to know is the memory is distributed, but you don't have to worry about the details, how MPI is implemented. And just remind ourselves again, these bulk synchronous machines and the idea of Richardson at the time, I think they look very, very similar. But this is not where the story stops. This is where I would say the clean story stops. And from now on, things become more and more complicated. So one of the things that's going on in CMOS is the scaling. And what most of you know is Moore's law, the doubling of the density every 1.5 to 2 years. But there was something else called Dennard scaling. And the way this goes is, again, when you have say you take a transistor and you have the gate width and you scale that with a factor alpha, it turns out, and you scale all the components on the transistor, all the physical components on the transistor, then you can also scale the voltage, and you scale the oxide layer, you can scale the voltage, and that means you will increase the density, you can increase the frequency or the speed of the processor, and you can keep the power density constant. And so you can increase the number of devices and you can increase the frequency until the oxide layer thickness becomes around 1 nanometer, and that happened about a decade ago. And then you can no longer scale because now you have tunneling currents that start to happen through this oxide barrier, and you don't have an insulator there anymore. And you cannot scale the voltage any longer. And so these things go through the roof, so the power density is not constant anymore, or you have to compromise on the frequency. And this is what happened. This end of Dennard scaling about 10 years ago translated into, when you look here, so what we are plotting is the dense transistor count on a processor. And so this continues to go exponentially. But you can see here that frequencies suddenly stopped scaling, and then the single thread performance stopped scaling. And then you see this increase of core count. And now even the iPhone has multiple cores on a processor. So that's the reason for this happening. And now what it means for the bulk synchronous model is that the compute components become highly parallel. And you can now think about some new abstraction, but it turns out the diversity of the components start to become very large. What I'm showing here is if you go to a talk by DOE, which is clearly the agency with the leading systems, at least in science, open science, then you would see these are the 3 large systems they have today in Berkeley, at Oak Ridge and Argonne National Lab, and this is what they have planned. So don't worry about the details, just that you see here multi-core processor, you see GPU accelerated system, and this is what is now then later called many-core processor. So you see different architectures. And if I put this in perspective, so these are the 3 systems existing today. I add a few from around the world that are also in the top 500 list, including, or top 10 list, including the one we run at the Swiss National Supercomputing Center. And then I add the new system. They are predicting Cori and some systems coming out in Japan, and then Summit in Oak Ridge and Aurora, these multi-100 petaflop systems. Then you see a trend in architectural trend, namely these many-core processors here on the nodes and these accelerated hybrid, which people, when they first came out, these machines said, in a few years they are gone, because this is déjà vu all over again. It turns out it's not the case. They are going to stay at least until the beginning of the next decade. Of course, the current multi-core systems will also continue. And what we see here is pretty much all the weather forecasting systems that I've been talking about. They are sitting on this more traditional line of computers, except for the one that we built and put in operation last year in Switzerland. So I will come back to this one. But the most important point is this architectural diversity is here to stay with us, and we will have to deal with it, whether it's good for our abstractions or not. Unfortunately, I would say, if you want to focus on just getting results out of the machine. Another thing that is bothering people is the power usage of these systems. And the most important lesson here is when you, so besides the architectural diversity, there is another reality that we have to deal with. If we want to be energy efficient, we have to understand where the energy is going. And then we even have to deal with what is happening on the processor. And this is just showing on 28 nanometer processors, but Bill Daly says this is the same story today at 15 nanometers, namely several orders of magnitude between the energy you spent on any floating point unit to do a floating point operation, and then just the moving the data between the floating point units, the caches, and then the off-chip memory. So the message to those who develop algorithms is we have to think at the same time as we think about efficiency in terms of computation, we have to think about efficiency in terms of not moving data around or keeping the data local. And this turns out to be a high priority, but a challenge from a mathematical perspective. The other thing is when you look at the physical dimensions of the machine. So this is this machine, Pete Stein. It's the one I have full access to any time. That's why I'm showing this, but the story is exactly the same if you're in Oak Ridge or Argonne or somewhere around the globe in China or in Japan or somewhere else in Europe. In our case, this is a hybrid system, again, that has Xeon CPUs and NVIDIA GPUs. And when I now put some of the numbers on here, the frequencies, this translates to cycle, cycle time of somewhere around half a nanosecond to just a bit over a nanosecond. And when we upgrade the machine, then the GPU will also be faster. So both will be below a nanosecond to do an actual computation. But if you're now looking at the dimension of the system and you have processors on one end and the other, the time it takes to synchronize them is, even if everything was perfect and went at zero delay, you still have to face the fact that the information cannot process faster than the speed of light. And so you have pretty much 3 orders of magnitude here between the time it takes to compute on a processor and the time it takes to communicate in the theoretical best case. So that is another reality that puts some people to question whether the bulk synchronous model is still good. I don't want to discuss this myself. We can maybe talk later. Or I know this is a contentious discussion, and I'm trying to avoid it here. Another one is, and this is really what also the Exascale initiative is coming to, is this question of Moore's law ending. And what I'm showing here is a slide, is a picture I took from a talk from Raj Hazra. He's the leader of HPC at Intel. This was a conference in 2010. So when Intel was right around 32 nanometers, and their Xeon processors, the way they introduce them is they do in 1 year, they introduce a new process. So they shrink the transistors. And then in the next year, they introduce a new architecture. So that's what they call tick-tock. And so this is what he predicted, Raj predicted in 2010, so here, that we would be in 2 years later at 22. In 14, we would be at 16 nanometers. Now, I know that I built a system with the latest Haswell processors that were not 16. They were 22 nanometers here in 2014. And actually, the 15 nanometer processors are coming out this year. So we can see from this prediction that used to be very reliable that we are already wrong. And the 10 nanometer is not really on the horizon at this point. So, and we, on top of that, we now even know Intel has announced that they are slowing down this process. So this really means that the end of Moore's law, we cannot just predict it when we see the size of the gate width or so, being in this range around 10 nanometers. At some point it has to end, but we also see it happening in economics. So the architectural diversity, I claim, is here to stay because it's a consequence of the task of CMOS scaling or Moore's law. And the implications, I'm not sure we understand everything, but we know that complexity in software is one because we can feel it today, and I will come back to this. But we also know the physics of the computer will matter always more, which is very good to the field that I'm most interested in. So the life of computational physicists, or I think physicists in general who deal with solid-state devices, will be very good in the next 15 to 20 years. And I think we will be back actually to the 1950s when the transistors were invented, because there was a problem with the tubes and vacuum tubes. So now let me get back to software. And this is not meant that you need to understand the details. These are the equations behind this Cosmo model that we are solving to do these regional forecasts. These are so-called non-hydrostatic Euler equations. The reason I've put them up here is just to make the case why intrinsically the software will be complex in these models. So there is no way around it, because you have various things. You have physics parameters that you have to compute even outside of these equations with solving other differential equations that are more local. And then you have different time scales that you have to resolve for horizontal advection, vertical advection, water advection, and then the fast sound waves. So you have to worry about different time scales, different algorithms to deal with this. So inherently, even though fluid dynamics is something we know how to solve numerically, or we believe at least at those resolutions, we will have a complex model and to code up. Compared to the many-body Schrödinger equation, where we are battling the complexity of the problem. We don't have really the same, this is all polynomial complexity that we are dealing with, but compared to the Schrödinger equation, the model is much more complicated. And so that's why in the end, the code that implements this is larger than most of your solid-state physics code. This one is a Fortran code, very well engineered, 250,000 lines of code. If you add some climate features, it can be about 1 million or 2 million. So a few 100,000 to a few million is the typical size of these codes. The problem is they are monolithic, and I will basically come back in detail to this, but so the challenge is really, this is the scale of code we're dealing with, and now we have many different architectures. So what do we do? This explains why the weather services are still on the conservative track in that other slide. But it is not something that has future. If they want to benefit from the performance increases, they will have to change to different architectures. And then the question is, do we have to rewrite these codes? And do we have to do it over and over and over again? And is this economically sustainable? Okay, so what I'm proposing is that we take a different look at the whole problem rather than looking at the lines of code. Namely, what exactly are we doing? Well, we have a physical model that I've been talking about, this example. We have equations that solve this model. And then we somehow have to write an algorithm to solve these equations, in this case, structure grid and finite differences. And then we write the code for this algorithm, we compile, and then we run it on a machine. And so this is a workflow that we have typically in computational science. And the reason this is very convenient to look at it this way is because we have, thanks to the von Neumann abstraction, this line that we can draw. And then we have one area where domain science and applied mathematics is dealing with, and then everything below the line is computer engineering. And this is, I've talked at length about this, but I can tell you it's exactly the same problem if you do material science and you solve Schrödinger's equation in the density functional mode, or it's the same thing if you do molecular dynamics. It's the algorithms, the equations, the algorithms change, but the workflow is always the same. And even when you do quantum many-body theory, it's still the same approach. So I'm going back to climate, but I could give the same talk in each of the domain. And certainly for material science, I can tell you in detail it's the same problem. Now the challenge we have is, as I said before, we have multi-core CPUs or we have these Intel Xeon Phi processors, which are not the same, despite the claims that Intel had until a few years ago. And we have GPUs. So are you going to redo the whole thing every time you change the processor? And the answer is, well, this is not sustainable. And so that's why we have to think about it. So what I'm suggesting is that we really reconsider these separation of concerns and, of course, the entire workflow. Now, what is common to all the domains, as I said, we have a physical model, a mathematical description, and an algorithmic description. We then have to write imperative code. We have compilers like LLVM that are actually quite nice and transparent today, but they don't do everything automatically for us. That's the one thing they don't do. And, but they do have backends for different architectures. And the very important point to realize is, in order to write efficient code to these different architectures, we have to change the implementation, and so the imperative code, and we have to change the algorithmic description. But nothing on this graph tells me that I have to change the model, the mathematical description, and so on above. So if you organize the work in this way, which is a perfectly realistic way, it's just not implemented right now in the codes, then it is obvious that you can draw a line. It is not good to partition this graph somewhere in the middle here, but you can definitely draw a line at this point, okay? And so the domain science and the mathematicians that develop model, if we could draw the line there, could be very happy if we give them a system and we take care of everything below. Obviously, so what I'm going to argue is that we need multidisciplinary teams that deal with this part, but and then at some point we use commodity components. So we have to draw another line between the companies that have the financial power to develop these systems down here, and then the scientists who have usually less money in any given domain, you know, and different budgets. But it is not really clear at this point where we draw this line. And so what we would like to have is a dynamic programming environment that is working at that high level, something that looks like MATLAB. And then we want tools that are basically enable this high performance computing. Now it's easy to draw it this way. I want to now, in the last 5 or 10 minutes I have, show you how this would be done in practice. And I'm going back to this Cosmo model, the model I've been discussing so far. One reason why we picked this is clearly because our weather service is running it and we had to solve a problem for them. But the nice thing about this is we're dealing with a model that's being used both by weather services and many academic research groups around the world. And the most important thing is it's a well-managed consortium that turned out to be very important if you want to understand how to make an impact with a new idea on a broad you know, a broad community. Having a community that's well managed to work with turns out to be crucially important. Now, going back to this thing, the 250,000 lines of code, you analyze how the different parts, the dynamics and the physics, the assimilation part, how they translate into runtime. And this is using this 2-kilometer model. Then you see, well, the dynamics is about 60% and physics about 20%. So 20% of or 40,000 lines of code amount for about this. Or you can say, you look at these two parts and then you cover about 80% of the runtime. Okay, so it's not very hard to say that if we attack this problem, we have to look at these parts of the pie. And then after long discussions with the community, we decided to rewrite the dynamics and to use directives so not change the physics code at the moment. This was a compromise we had to do. And just from a point of view of when you rewrite code and you have a very good programmer and you're set up with unit testing, regression testing environments, you turn around 20 to 25,000 lines of code per year. So 40,000 lines of code is about 2 man-years that you have to invest in rewriting. But that's not all that we want to do, just rewrite. We also wanted to learn something and to deliver tools. And so one of the motives, I showed you differential equations with lots of operators. And if you do solve this on a structured grid with finite differences, you end up with motifs that look like this. So this is, you have some point where you have a field and you have to take the differences to the neighbors and update this point with the field. This is the two-dimensional Laplacian in an example. So input data and then the output data here. And this is now translated into code. The code that implements this Laplacian is this here. So you have a loop nest and then you have the piece of code in the middle. The problem with this is you saw the equations. We have many, many of these operators. And so this code is repeating over this type of code, but always with small differences in the data. And so it's just repeating over these 40,000 lines, or creates these 40,000 lines of code. And there's not much you can do in terms of a traditional library call. Or so you just, that's what you have. Okay. Now, how do you create a library nevertheless? And this is what people have been thinking about, is to have now, instead of a general library, or general software, you have a domain-specific library. And there are a number of approaches that you can take with source-to-source translation. So the idea of this is always to have an interface that looks more or less mathematical to the programmer, and then somehow something that generates code behind it. Now, the choice that we took is this embedded library in a host language like C++ standard template library. And I'm going to briefly show the ideas behind it. So the problem you have to do is you want to separate the loop logic, which is somehow tied to the grid, from the actual formulation of the operator in the middle. So these are the two problems that you have to separate, and you can't in a traditional language like C or Fortran. But using these template metaprogramming constructs in C++, again, the details don't matter. The results is what matter, is that you end up having the description of the stencil, which here is just a normal C++ functor. And then you have a templated construct that deals with the mesh, with the grid that you have to deal with. And so the part that actually makes it domain-specific is this mesh. And once you have these ideas, then you need a model, a decomposition model. So how you are going to decompose your application. In this case, we're talking about domain decomposition. So you have the typical compute domains with the halo exchanges that you put on different processors. And then you subdivide this, in this case, into blocks. And then the blocks again into finer grain threads. So these could be coarse grain threads or tasks, and then fine grain threads that map onto a vector machine. And so taking this abstraction that is not completely general, it's very much tied to these type of structured grids, but maps onto different, so multi-core processors or GPUs, so SIMD or SIMT programming model, allows you to keep the same front end but have different backends. And so the code goes from a monolithic code that we had before we did the refactoring into a well-structured code, at least for the dynamics that we were allowed to rewrite. And we ended up, and then we have these two different backends, and we can add a third one now for the Xeon Phi processor. It's coming out this year. So we can support different architectures with the same set of tools. And the tools are general and migratable to at least architectures that we foresee coming. So if I now put this code fragment or this dynamics onto this plot here, when I'm talking about domain-specific tools, it is these tools that we need to be developing and investing in. And then we want to get rid of the Fortran or C there, so we want to go into IPython or Jupyter notebooks to have an interactive environment. And as I said, the same thing applies to other areas like material science. And the question is, how do we pay? Now, that's the last thing I want to discuss, is how do we pay for this? The example that I gave, the investment was about 2 to 3 million Swiss francs that we invested over about 4 or 5 years. And I told you MeteoSwiss is going from this 2 kilometer resolution runs to introducing 1 kilometer, these ensemble runs, and had to improve their assimilation. So what they wanted to do over the course of about 3 years between the machine that ran this one to the new machine was an improvement in 40 in the size, in the performance of the simulation. And if you look at this in conventional terms, so not working on the software, this is our machine room, that's the machine MeteoSwiss had. Now you can do estimates from spring of 2012 when we introduced the machine that was running up to now to the second quarter of 2015 when they needed a new system. They need a factor 40. Let's say the Moore's law gives us a factor 2. So we are a factor 20 in the size of the machine. Or the number of x86 sockets. Now I can give you a reference. This is a Cray XC30 system. So we want, this is 40 cabinets. We want 30 of these cabinets. So that's what the system would look like in the machine room had we not done the software investments. And the footprint of the machine is roughly the investment you have to do in hardware, and also the power bill is proportional to the footprint. And so clearly this would blow the budget of MeteoSwiss apart, or they would have to find more funding. And so thinking inside the box was not an option, and that's why we did all these software things. And the result in the end is a machine that is loaded with GPU, and so it was in the end different from the ones other weather services would run. And the interesting part is if you now compare where did the performance come from. So the footprint of the machine in the end is the same as the current one. And since we have the old code that is still being run in Germany by the German Weather Service, we have the new code. The new code runs on different architecture. We can make a number of comparisons. And we can then say that just the processor performance, so Moore's law, gave us almost a factor 3. So factor 2 was a bit pessimistic. Then improvement in what we call system utilization really has to do that MeteoSwiss figured out that they can run most things instead of double precision, they can do single precision. But they did it in a very controlled way now because we had just rewritten the code, so we knew everything, where things were going with the precisions. It wouldn't work if you would just turn, double to single in a legacy Fortran code. Then you have the general software performance. That's just taking the new code running on a traditional architecture gives you almost a factor 2. Then the ability now that we can go to a new architecture is another factor 2. And so you compare Moore's law against what you get just out of the software. And then we had to increase the number of sockets. And that's how we get to this factor 40. And the nice thing now about GPUs is that it's a few more sockets. The integration density was a bit higher, so the footprint is the same. But the energy is actually lower, significantly lower. And so in the end, the machines are about the same size, and the energy to solution is for the new problem is somewhere around 30% less. And if you now do the math, that covers many, many times the investment that we had to do in software. Finally, I want to acknowledge some of the climate scientists that have been bugging over the many years in helping me understand what the real problem is here. And I think this is one of the big issues that we have in computing, namely in order to solve or build some of these systems, you really have to understand both the computing side. I had the fortune at Oak Ridge to learn that for a few years. But then if you have to work in a domain that's not your own, and so most people are very, you're always limited to what you know. And so you have to have access to people who have an interest, good scientists who have an interest in actually investing in some of their time in building computer architectures. And I think that's the last message that I want to give to scientists, that if we want to improve in the future, we actually have to make an investment, and we have to work with people who understand computing. And so I thank you for your patience.